Okay, so this work was done with Shirin Sohrabi, Octavian Udrea, and Dominik, who was a summer intern at IBM Research at the time. Okay, so as everyone probably knows here what FDR is, you have multi-valued variables, actions that change their value, the variable values, non-negative cost, initial and goal states are full and partial variable assignments, and cost optimal planning is about finding one sequence of actions that will take you from initial to some goal state and minimize the cost of the sum of the actions. So top K planning is about finding a set of size K of plans that there exists no plan outside of that set that will be of smaller value, of smaller cost, sorry. If you don't have enough plans, then just take all the plans that you have. So how do you solve those tasks? So there is a search algorithm called K-star that was invented in 2011 by Ali Jazar and Liu. And it was adapted to classical planning by Sohrabi, and Udrea in 2016. It works basically in two phases. First, it develops part of the state space with A star. Then it runs DAX around that developed part, checks whether a sufficient number of solutions of top quality are found. If not, it continues to develop A star to the further layers and so on. Another possible approach is to use existing optimal planners with iteratively forbidding previously found solutions, and that was done previously by just finding one solution, taking that solution and generating a solution of length n, and generating n tasks where in the first task you forbid the first action at the first place, and the second task you forbid the second action at the second place, and so on. And then the union of the solutions to all those tasks will basically forbid just one solution. Right? So what we do here is we basically make one reformulation that will result in a planning task that forbids one or a set of solutions. And then what you can do, you can take your favorite cost optimal planner, you find a solution, you possibly extend it to a set of solutions, you forbid all of them by reformulating a planning task into a new planning task, and again you find a solution, and so on until you find enough solutions. And if you use an optimal planning, you actually guarantee that that way you get top K solutions. So an additional contribution was to actually take K-star and implement it in a PDDL planner, because the previous implementation of K-star is implemented on top of SPPL planner, which is a dialect of PDDL, but we could not actually run that on IPC benchmarks. The benefit of actually implementing it in PDDL planner, and in particular in fast downward, that now we could use heuristics from fast downward, basically, and we can base our implementation of existing code on A star in fast downward. So how that actually works? So basically, given a planning task and a plan, you want to come up with a new planning task that forbids exactly that plan and preserves all other solutions. So we will take the variables of the original task and add additional variables that would be binary here that would encode somehow whether we actually following the solution or not. And I will not focus on the initial and goal values on those variables, maybe on one of them. So basically, the variable v overline will encode whether we actually still following that solution. So it will start from 1 and will require 0 in the goal state, in addition to all other goal states of the original task. Sorry, goal variables on the original task. Now we need to extend our actions. So basically, we will take the actions and we will encode them in 4 different ways. So the first we'll take those actions that are not on the given optimal solution or given solution. And then we'll say, well, if we run those actions are not on the plan that we need to forbid. If we apply that action, the outcome would be to turn this variable, to set that variable v overline to 0. Now we achieved our goal to divert from the plan. The next set of actions would be actions on plan, and they will encode actually following the plan. So they will change those variables and basically propagate the token from from vi minus 1 to vi. The next set of actions would be actions on the plan, but applying them would actually divert from the plan, because that's not the right place to apply them. That's that particular action actually exists on a plan that it should have been on a different place. And the last part would be actions on the plan, but you already basically diverted from following that plan. So just continue. So then, well, simple algorithm that actually gets solve stop k planning would be take the original task, find a solution, find a solution with your favorite optimal planner, forbid that, and continue until you actually have enough solutions. Or if your optimal planner actually reports that the task is unsolvable, then you know that there are no other solutions exist. So we can get one solution after another, but we would like to get more, right? So given one solution that an optimal planner returns, we want to have a good way to actually quickly extend it to a set of solutions. So one way that we can do it with is structural symmetry. So structural symmetry that stabilizes initial and goal state will map any plan to another plan of the same cost. Another way would be reducing orders in that plan. So basically reordering actions in the plan. So we could think of several ways of doing that. Could be done in a naive way. It could be done in using the concept of action independence from partial order reduction. So then what we can do now, we found a set of plans. So we found one plan extended to a set of plans. Now we can actually forbid a set of plans. I will not show that reformulation, but it's really similar to the reformulation of forbidding one plan. It's actually So one way is actually forbidding one plan and reformulating that, and then forbid the next one, and so on. So basically apply one reformulation over another. And another way is actually reformulate the planning task to forbid the entire graph of possible found plan paths. So how does it work? So this is any k basically coverage. So this x-axis actually shows the k, the values of k, possible values of k, starting from 1 and going all the way to 10,000. And the y-axis shows the number of tasks for each k plans could be found with different techniques. So the horizontal lines represents k star with blind heuristic and IPDB heuristic, and the other 6 lines represent using structural symmetries or not using structural symmetries, and the 3 options of not extending with reordering, extending using a naive technique, or extending using independence of operators. And as you can see, it's really beneficial to rather large k techniques to use the iterative approach. So rather large k values. So focusing mostly on the large k values, there are basically almost even partitioning of domains to which the iterative approach excels and versus the k-star approach. So I show here only the domains for which the difference in coverage is larger than 5 for the k equals 10,000. So as you can see, so this one is in favor of the iterative approach, and obviously if you have k, smaller k, you can get better coverage, of course. This set of domains is in favor of the k-star approach. And here as well, I'm showing only those that the coverage is larger, the coverage difference is larger than 5. So they are quite complementary, I would say. Yeah, so you have a variety of approaches. If you need to get more solutions, many solutions, then you have a choice to make, and that choice would be per domain problem. So to sum up, once again, we are using classical planners to solve the top k planning problem. We suggest an anytime approach that can dump plans as it finds them, and it performs pretty well for medium to large Ks. So it's, again, it's really depends on how you actually measure what medium large is, because usually in planning community you are not, up until now we were not looking for thousands of tens of thousands of solutions. So the downside of this is the size of the reformulation actually grows, of course, with every new iteration that you perform. K-star works pretty well when you actually need a huge number of solutions. The problem here is that K-star actually finds almost all solutions almost simultaneously. So basically, it's a huge, lots of time until the first solution found, and then almost all solutions are dumped at the same time. So in our experiments, almost everywhere, K-star was able either to find all solutions or none. So for future work, we would like to look into other techniques for deriving solutions from already found ones without actually performing search. For K-star, there is a requirement for consistent heuristics, and at least theoretical in the original paper. I'm not sure whether this actually is a requirement or that was made in order to make their lives easier with the proofs that they provide. So we are looking into that. Maybe if it is an actual requirement, whether we could adapt the algorithm in a similar way that A-star is adapted to non-consistent heuristics. And another possible future venue for K-star is looking into pruning and safe pruning for K-star. So, thank you.
Okay, do we have any questions from the audience here? Ah, there we go. You're monopolizing the questions here. Okay, I have to not hit the camera. Oh, very close. Ah, not even close. David, you have to save me here.
Great work about the consistent heuristics. Can you not make any heuristic consistent using bidirectional path maxing for A star?
Okay, so what do you suggest to take?
There was some studies about how making inconsistent heuristics consistent, by studying how the values are evolving, and then based on the parent value, you can guarantee that it cannot go lower than the action cost, and that way you make things consistent. No?
Yeah.
So you can make an inconsistent heuristic into a consistent one, right?
Are you suggesting to adopt the heuristic itself that way? So that was tried, I think, was.
Yeah, it was not.
Okay,
I was
so
just wondering
yeah.
if you could use an inconsistent heuristic using those techniques, because they're saying K star requires consistent
Yes.
heuristics.
So you could adapt the heuristic to actually become consistent, like LM cut could be adapted to become consistent. I think that will take some overhead. I guess didn't pay off for A star, but
it was good for ID star. It wasn't. So it was neutral, no, for A star, I think.
I don't know. So I think Florin is there, right? Was there? Okay.
Yeah, but just if you cannot use them at all, I mean, you might be worth studying even with a performance drop
right.
to be able to use the heuristic.
My hope is that this is not actually a requirement,
Okay.
and that was just to make the proofs easier. I'm trying to prove that, and I have no proof yet. And if not, I think something like reopening could also help.
Okay. Thank you.
Do we have another question? Oh, there we go, way back there. This is a constant entertainment here.
Thank you. You're looking for the sort of a set of K different optimal plan or best plans. What exactly is the criteria for plans to be different?
Sequence has to be different.
So if you have 10,000 permutations of the actions in the same plan, that's the 10,000 different plans you will get.
Yes.
So is there a way to adapt either the encoding or the top K algorithm to consider sort of more intelligent notions of difference?
Yeah, so currently I'm trying to derive reformulation that will forbid the partially ordered plan. I think I'm almost there.
I had actually a question almost identical to his. Let's suppose you had a distance metric and you wanted to generate your K plans that had a minimum separation of distance.
Right, so there is a whole field of diverse planning that people are trying to do that. And the way that most of them are doing it is by tweaking heuristics and stuff like that. So they basically find some plans and they tweak the algorithm to perform slightly differently, and to behave slightly different, and then they hope that they will find the next plan that will be different from the previously found one. But that
really
actually can help them, right? So they can actually stop tweaking the algorithms and just run the new one on the new task that forbids. So that would actually require what you are asking for, Patrick, to actually forbid all the orders.
Yeah.
I think I'm almost there. We could talk from us.
Okay, maybe one more question. Can you?
I'm sorry.
Can you talk into the box here? Like now?
I was, sorry. I think I recall a paper from ICAPS 2014 where they were trying to define some notion based on landmarks, some kind of actual meaningful distance from an existing plan. So that might partially answer that question.
Okay, great. I think this is a good topic that maybe we could also continue offline. Why don't we go ahead and go to the next speaker, and I'll try to catch this. Thank you.